Hi, everybody. It is July 20th, week 5 of the summer term, right? And we're going to be talking about some stuff before the project. So let's start off with a email I got back from the IEEE club, Drexel IEEE. He actually put together a document. I asked him to, and he did it. So we're going to look at what he has in mind for the event. So I think he wants it to be as translatable to what we're doing as possible. But to do that, he also needs to set up stuff for their club as well. So they've already detailed the main track that the RC car would go around. Pretty cool diagram. And apparently they use something from NVIDIA's Jetson AI race. So I assume that this track is something that many people use because NVIDIA is a pretty big company. And so there are 12 orange traffic cones inside every curve. As shown above, there will be one obstacle cone placed at random locations on the track. The track is equipped with a minimum 1 meter of space along each section of the track, so 1 meter width. And there's no separate training track leading up to the Grand Championship. The main track will also serve as the training track. Okay. Mentions the idea of random cones. So test the models competitors are using for edge cases. Okay. And for the event, it looks like he would want to do something like a hackathon where people can build and train their cars and systems. You can reserve the whole track for training, first come, first serve. We can have more than 2 sessions consecutively. I've myself never partaken in a hackathon, so I think this would be really cool because it's kind of the intersection of what I imagine a hackathon would be and a true engineering project. Got a chat message. We are not hosting the event, Andy. This is an event that we'd be co-hosting with IEEE, and we'd be working with them in teams. So my idea is that one person or a couple people from Drexel AI would be working with some people from IEEE in the fall term. And this is the equipment that they're looking at. Raspberry Pi, RC car, battery. I don't know what this is actually. Donkey car kit. Okay. I've never done anything with cars before. This is all pretty new to me. About 200 per car, which we have the funding and so do they. Okay. So yeah, I think this would be pretty cool. It's just about figuring out how you'd actually do this.
Yeah, I think in the document it says like, I guess like if you scroll down, the coding part of this would be like PyTorch or TensorFlow or something. The RPI number 1, the few purchased. So I guess that's cool, but I guess where the autonomous part comes from.
Yeah. I've never dealt with that kind of data, so it'd be interesting if we'd have availability to that kind of data beforehand, instead of just getting instead of relying on the sensors that the IEEE guys put on. I imagine that people who are in IEEE who are kind of savvy about car autonomous RCs or autonomous cars kind of have an idea of what features cars record and what sensors they're going to put on it. So maybe we can communicate with them where they're the user, and we can kind of figure out what features we'll have availability to, and how we implement it in TensorFlow. Oh, that's pretty powerful. Okay, supports TensorFlow and PyTorch. Cool. So yeah, I'm looking forward to this mostly because I've never done anything like this before. I've never done stuff with computer vision. Most of my work is in bioinformatics, so this is new. This is very new for me. Are there any questions that you'd want to know from? But I mean, we're still like months out from the event. But are there any questions I could email him again? I assume that they'll take care of the funding. I'm sure that we could talk to Professor Kim or other people in the engineering school to just to get this per team, because I feel like this is pretty important. We can plan the location of the event. Oh yeah, I don't know. I'd imagine that we do something in the engineering building with Lee. Where would it be? Yeah, that's a good point. So yeah, still in early phases. I was pretty happy that he was able to put this together. Cool. Another thing, I got an email from the Women in Computer Science Club, and I've never been to any of their events, but they have this alumni and mentee program. So Alicia, are you in WISC?
Yeah, I've been to some of their meetings.
So is it only girls, or are there guys there too? How does it work?
I think some guys come to the meetings. I think it's mainly like they mostly want women, I guess, but I think they're like open to any. Yeah. Like some of the events, like I know, like I think tomorrow they have like an event for like quantum computing with Mark Bodie, if anyone knows who that is in CS, but it's usually open to anyone.
Yeah. So I think this would I sent out a mass email yesterday or 2 days ago or whenever I got this. Yeah, yesterday. And so it would, I think the mentee and alumni and what they're thinking about for like professional development would most likely involve the females from Drexel AI, hence it being, women in computer science. So yeah, to those who it applies, just this is for your information. And the email was sent out yesterday. So cool. So what have I been doing? So I went on to, we look at the GitHub. I don't think I pushed my changes, but we can check. I worked on a function that would allow you guys to get the data. And this is pretty important because then we'll all be using the same exact data set when we're testing this out. I'll just show you how to use it. Okay. I'm not sure if it's pushed. It might be. So if you go in algorithm, it's in load data. And this is pretty small. All you're going to be doing is you're going to go into, going to open up Python. After you clone the GitHub repository, run algorithm. Normally what you would do is you data and then tempter. So data is a NumPy array, 2D NumPy array. Tempter is a string which represents where on the computer it downloaded the data. And you're going to just call load data with nothing in it. After you run it the first time, you can store temp data, tempter, and then you can use it in subsequent runs of load data. And that way it won't re-download the data. It'll just store data in the data file. So if we look in data, that's it. You can specify the shape of the data using some arguments. So for instance, load data has a number of samples and number of points. So I want 100 samples with about 10,000 points each. And now we have our data set. I created another function called getSegments, and what this returns is xtrain and xtest, which would be our regions like here, the n right here and the m right here. This would be xtrain and this is xtest. And you just do getSegments, and you give it data, and it splits it up. xtrain.shape, xtest.shape. And what it does is it uses n train points and n test points, and it basically generates a random variable to cut the data so that you're grabbing 50 in xtrain for the first sample, you're grabbing 50 random points, and then the next 20 points are stored in xtest so that they're always next to each other. And for the data set, we have 520 points for each sample that are adjacent. There are some issues I noticed. For instance, in the data, there are like positive and negative infinity, and then also NaN. So I used a function NaN to num to just replace those and set those equal to 0. If anyone thinks of a better way to ensure that there are no NaNs, we can do that. I already explored looking within the same sample for a region that doesn't contain any of those values for, in this case, 520 consecutive points, but that didn't work because it took too long, and I guess they're just way too common. Another option would be to set them to the mean, and I could just replace this 0 with like mp.nan mean, but I didn't find an easy way for me to calculate the mean of a lot of values without getting and getting rid of the positive and negative infinity. So I didn't want to deal with that yet. I'm just going to leave them at 0 for now. These values are pretty large, so maybe, I don't know, putting in zeros won't. I mean, it's going to be pretty drastic. So we probably should find a better way to do that. And then Osamu gave me the sparse representation code. I haven't figured out how to get it to work yet. The idea is that he has a model.py right here. And in here, he used TensorFlow to build an activity class, a dictionary class, and a sparse model. And you can define these classes using different variables. So we're looking at data size, which is just the number of samples we have. Sample size is the number of points we have. Batch size is the number of batches we want to use for training. Sorry, that's the size of each batch, and then you can find the number of batches by just dividing the size of your data. In our case, it's going to be 100 by the batch size, which is 10. So our number of batches is going to be 10. And then we're building these patches per image. So we're going to have 50 patches, and each patch is going to be, really they should be 50. Let's do 20 patches per image, because it has to be an integer multiple of both the testing and training set. And then you can figure out how big your dictionary is going to be. So in our case, right, we're going to have 20 patches per image. So for the first image, we're going to have 25 dictionary filters to describe that image. And then you can also define the number of filters. These are values that correspond to the sparse model. So alpha is the learning rate. Beta is related to these values A, B. I'm not sure what those are yet. We can actually look into that. So beta is in dictionary. Dictionary is in here. Beta is in here. Self.beta. It's taking from Keras layer. Super dictionary. Let's actually look that up. I'm kind of curious. Keras layer data. I think it's just a regularization parameter. Beta weight. Okay. Interesting. And then epsilon as well. And then some epoch and number of layers here. So just in case anybody wants to maybe help out with this and try to debug it, but what's happening is when I run this right here, when I run all of this right here, I get the segments, I forget. Yeah, I did. Chat. The way to visualize the data. There will be, and I can actually show you a pretty cool way that you can visualize the data from what Osamu did. Osamu's pretty good at this stuff. We still have to learn. So that's the sparse model is initialized, and I get an error whenever I run the sparse model. Oh, shut down this. Okay, I'm gonna run Jupyter Notebook, and we're gonna go to sparse minced. He did it on the minced data set. And I've been trying to follow this along with an example he used on EEG signals. So he ran the sparse model here, and then he was able to visualize the filters. So you can see that those digits, those handwritten digits, data set. In case people aren't aware of what it looks like, the data set is a aggregation of digits, handwritten digits. The idea is to classify them into 10 categories. And so right here, you can kind of see these features arise, which describe the edges of the data. So maybe this is like a 0 or something, or maybe this is a 9, this is a 1. And then you use these filters to reconstruct digits. And then he did the reconstructions here. So this sample was reconstructed into this. This sample is reconstructed into this, which is pretty interesting. So I guess if you want to go back to our project, the idea is that we'd take input values, and then these reconstructions wouldn't be based off of the values that we're training the dictionary on. It would be based off of the predicted time series, and whichever matches the dictionary the best, whichever has the best mapping to the dictionary or best uses the dictionary, would be classified as the best child in a genetic algorithm by iterating over so many children. So what I've encountered, that's not this, what I've encountered is that when I run it, I get a, it complains about the activity weights. And for some reason, when I look at the activity weights, they're NaN. Right here. And my hunch is that they shouldn't be NaN. And it even tells me that they shouldn't be NaN. It's even more surprising because when I initialize the activity weights like this, they're non-NaN, but when I run it, they go to NaN. So I think it has to do with something with some of the values I initialized. So I have a feeling that I just have to do some digging and some learning and bother with Samu some more. Any questions about the progress that we have so far?
So have you tried running this like with the Samu's sparse representation?
Sorry. So yeah, this module is a Samu's, and this is my attempt.
Okay.
Yeah. So I have to figure out what's going on. But we aren't stuck. We aren't completely stuck because as we're doing this, to sparse series, add it, add the updated version. Now it's on GitHub, so now you can git pull or git clone and have the updated version. We're not all lost because some people have been looking at the paper. I put something in the Slack channel this morning because some people have been asking me what I have in mind with the paper. I mentioned that we need to look at the background section. We need to talk about sparse coding, time series, and genetic algorithms. I think I actually didn't include sections, but I think it would go under the background right here. So if we go under background, subsection, I started limits. Yeah, I saw that. I wasn't sure who that was. I appreciate that, Andy. You can do me a favor and just put your name up at the top. After, we'll probably have this in alphabetical after mine. And then I don't know what college you're in, maybe CCI. Suffolk, I think you're in CCI, so you can put 2 in addition to 3, because you want to include that you're
actually doing like custom design, so
okay. Okay, sure. If you're in multiple colleges, just put 2, 3, whatever. It's always good to have those associations.
Take like 6 colleges.
Oh, okay, yeah. Well, that's funny. Okay. So we're going to start with sparse coding because I think that's the easiest thing to do. We need to introduce sparse coding in the background. So this section is going to be like an introduction. Sparse coding and how it's used in image processing. It's not too terribly popular in terms of signals, how we use them. So I think that we're going to want to talk about that in the method section, or actually relate to previous attempts at waveform data. Next, we're going to talk about time series forecasting. Actually, I don't know which one should go first. I think time series forecasting should go first. Introduction. This would include what you presented on, Alicia. Introduction of time series forecasting. I think it'd be really cool to make a distinction between like multi-step, single step, and multivariate, univariate. Talking about those different distinctions.
Someone asked in the chat, are we linking other papers that explain?
Yes. So
yeah,
what I had in mind is any time that you work in the background section and you look for what we call related work, save that maybe in a documents folder, and we'll add that in the bibliography section. I'll have to add and format that. You could even go as far as sending the paper in the time series chat, and I can show you how to link it up to the paper so we're all on the same page. You're just going to cite it, create a citation, and then use.
Like we could just like download the BibTeX and put it in the reference like directly. So
yeah, you could also do that if you are familiar with the BibTeX. I was going to do that. That's what I've been doing. I've been going through and adding it manually, right, like this, for other papers I'm doing. Okay. And then this should also include related work, popular models, off-the-shelf models, stuff like that. Alicia, do you have a model in mind that you'd like for us to use?
Yeah, I was working on just the basic LSTM model. Okay. I was gonna add my pull request like later today.
Yeah, of course. I look forward to seeing that. The idea is that you'd want to do like build model, and then predict forecast. There might be some other schema that's better.
Yeah.
Cool. And then the next one is I think this flow makes sense. Time series. So we're basically predicting signals in time, but we're also creating a sparse representation of it. And because there's no easy way for us to do gradient descent, we're using it. We're using a genetic algorithm to handle that. So this can be like a brief overview of Genetic algorithms, those with some related works. I think GANs fall into this category, but we don't need to really talk about that because it involves, that gets pretty complicated. I like how you included the, I like how you included this, Andy, right? It was Andy, make sure I got that correct. Yes. I like how you started with that. It helps, bring the paper up to speed. Cool.
I have like I've collected the background for genetic algorithm and sparse coding, so I'll put it up later tonight.
Do you want to share your screen?
Oh, it's in a very messy condition right now.
Okay. Okay.
I'll just put it up here.
Yeah.
Overlay.
You know how to do that with the, how to do that in LaTeX?
Yeah, I know.
Okay, cool. Yeah, so make a headway. It's week 5, no rush. There is there's abstracts due to a conference through Temple, but I don't know if we should target that one. It's because it's due August 1st. But we'll target another conference after we get results. I'd rather target it at a so like with undergraduate conferences, for those who don't know, okay, step back. For people who haven't done conferences before, there are like undergraduate conferences, but then there are study specific conferences. I've been to both this past year, and you typically get more out of the field or study specific because more people kind of have the background you do. There's less people, it's a little more competitive. I've been to a couple like general undergraduate conferences, but the categories are kind of very, very sparse. They're very sparse. You have humanitarians, environmental engineering projects. So there's like no overlap, and people just have varying amount of interest. So I definitely want to aim this at at like a field specific or topic specific conference. Cool. So I had someone, I know this load data, I'm really hoping this works, but I know this works on Mac because I tested it myself. All it does is it creates a temporary directory, and I had tested on Windows, and I think it works. Basically, I do a platform detection, and then depending on one or the other, you're going to use WSL or wget. If you get an error saying this doesn't work, it's probably because you don't have wget or WSL installed. You can just like Google that. In my opinion, this is a very good programming practice whenever you're downloading data and you're like giving it to many people, and you don't necessarily need to keep the data in your memory or on your computer for a long time because you're just going to run a pipeline and get results, and you don't need the data. So storing it in like a temporary directory through this, like listing this algorithm or this procedure I think is a good practice. Because I know I always have too much data in my computer that I don't necessarily need for a long time. It also helps with reproducibility because anybody can run this off of GitHub, have our raw data, and understand how to process it like we did. I also did some thinking about the score function, and I'm not sure that I explained this as best as I could. So I think we should go back to the drawing board and work it out together. We have some time. Before I do, is there any questions about either anything I introduced in the beginning of the meeting or the progress that I'm hoping to make, or what people can do? Okay, cool. I'm gonna stop sharing. I'm gonna go to my whiteboard. We're gonna talk about this. So actually, we're not gonna use this whiteboard. I found I don't have Microsoft, so it's been pretty frustrating not being able to use MS Paint when I see everybody else using it. Kind of felt left out. Found my own MS Paint. It's called Klecky. I don't know, but it's cool. So we're gonna deal with a signal, right? Some random signal, and then we're gonna say this is the barrier, and we're going to use these first n time points to create a sparse representation that we're going to use to compare the prediction of the next n time points. Okay. So we're never actually going to use these time points right here. What we're going to do is we're going to pretend that these time points don't exist. And we're going to train our LSTM model and our sparse network on this model, and then do some sort of forecasting, right? And we're going to apply the dictionary we learned from here. So this is going to get some dictionary D, that's sparse. And we're going to say, okay, can you reconstruct, can D be used to reconstruct this image well? So we're basically going to use the reconstruction error as our metric. The idea is that if our sparse model, if our dictionary can reconstruct this well, that means that this input signal that's in pink is close to that here. So what people often do is they take like their input signal X. It's terrible. They take their input signal X, and then they subtract the dictionary elements by the activity. And then they square it, and then they do some like regularization on it, like there's another regularization parameter. And this is going to be the reconstruction error that you use as a score. Is what in M already created before the sparse coding M? So, okay, good question. That's actually a good, I'm glad you're asking questions. That makes me very happy. So M isn't, M, so the idea is you take N points, you train it on two models, the LSTM model and the sparse model. So if we look at the time series model first, you're going to use the LSTM model that you trained on N to predict the next M points in pink. And then you're going to use the sparse model you trained on the first N points to reconstruct the pink image. So then like what you predicted is going to serve as the input to the sparse model. And if the reconstructed image has a high error compared to the if the reconstruction and the predicted, if the reconstruction of the predicted values and the predicted values are close to each other, that means that the predicted values matches the dictionary that you learned, which means that we're getting closer to our time series forecasting model is improving. And so what I imagine will happen is we'll take, can I make this bigger? I haven't tried that yet. What does this do? Oh my goodness, okay. Is it like an extension or something? I'll be pretty upset if it's pretty limited. I know with MS Paint, you can just like fit. Okay, it's only one page. Layers. This is the first time I've ever done this before. Layer 2, delete. Okay, well, I'm struggling. What I imagine is you'll have some vector. You'll have two vectors, one right here and one right here. This top vector will be associated with, pink actually. So this top vector right here will be associated with scores right here. And then the bottom vector will be associated with weights that led to predicting this value. So these weights are going to come from the LSTM model here that was used on the region N. And by having this mapping, we can say, okay, in the first generation, we want to pick the top 5 or the top three. Let's say the top three. We're going to pick the best three pairs. This one's the highest. This one's the highest. And this one's the highest. These are the top. These are the best. So in our case, the lowest scores right here. These are the lowest scores. And then we're gonna use those lowest scores to find what we imagine to be the best weights. And then in the next generation, we're gonna randomize those weights and use them and do this process iteratively. So really, our score function isn't anything Euclidean. Well, it kind of is. It's really just this mean squared error right here. If you go back to the function we were using, we were saying you could use a variety of different functions, but really what we need to look at is the activity, the sparse activity, and then the dictionary. So what I imagine we'll have is really our scoring will be sparse activity and then sparse dictionary. And we'll just simply want to return this function right here of the sparse activity and the sparse dictionary. It won't be this for the simple reason that, it won't be that. We actually need the input as well. Cred. There we go. I'm actually not sure how to do that right now because I imagine this is two-dimensional, this is two-dimensional, this is two-dimensional. So we need to get the reconstruction. So we're going to call that R is equal to this times dictionary, and then we're going to return the matrix Euclidean distance. And I don't know how to do that yet, but I think I can Google that. So then, it'll go like something like this, where you have red minus R, and that'll be set to the error. Return error right there. Yeah, and I think that's what we're going to want to do. Or we might take after this right here for what we're doing. We don't need these functions. Yeah. Does this make sense? What we're doing here? Each score, which is just the reconstruction error, X is the predicted region of M. D is the dictionary from N, and A is the activity learned from the dictionary D. A is the activity A is the activity learned from reconstructing the pink right here. So obviously, I know I hate to beat a bush, but obviously this pink one isn't nearly as good as if we got something right here, right? The reconstruction of the green one would be a lot less than that of the pink one, and thus we choose its weights, and we'd use that in the subsequent generations. Cool. Oh, we're getting closer. I just have to figure out what the heck's going on. I'll definitely need to call Osama because it's his code and he understands how it works better than I do. Cool. So does anybody have any questions in regard to this or the paper? Siabiek. When should the paper be done by, Andy? Ideally, I'd like it to be done by the end of the term. So we have 5 weeks, which I think is pretty doable. I know we're making slow progress. I'm just presenting on some functions I did, and it's good because I'd like people to kind of digest the algorithm and be able to understand what we're doing here. I'd hate to just come up with something and then you trust that it works. So I think I kind of want all of us to understand it together. If anybody wants to take a crack at the algorithm section, you can also do that. I tried to outline it here. I know this isn't in the GitHub, but if you'd like to try to explain the algorithm, then I can send this to you and you can start on that section. I think we asked these questions 2 meetings ago or last meeting about what we're doing, and we've been answering them. So let's go through them just so we're on the same page. So what data are we going to use? We're going to use ECG data. We have the ECG data. We have the ECG data now. I have a way for you guys to download and segment it such that everyone will have the same data. How do we find the sparse representation? Well, we have a SOMWIZ module, so this is close to being done. How do we define our scoring function? Our scoring function is defined based on the reconstruction error of the predicted image in M and the dictionary learned in N. How do we do the multi-step time series? How do we generate the multi-step time series forecasting? I think Alicia mentioned we're going to be doing a LSTM model. And then how do we ensure that all K children are different? How do we track their weights? That's something I haven't really thought of. So Alicia, I imagine that there is some sort of randomness associated with each trial run of the LSTM model. Do you know where would that be stored? Is that stored in like the first layer, or is it like the initialization? Like you can like have a bias of weights, right?
Yeah, you can. Yeah.
Okay. So if you're making a pull request, it'd be great if you could return the predicted like if you're gonna have a predict function, return the predicted xpred predicted signal in addition to the weights used at the beginning of the model.
Okay.
Because what we're going to do is we're going to compare. We're going to use that's going to like xpred. I've only ever heard of ypred before, but xpred is going to be what we compare to is what we use for the sparse coding, and then the best scoring xpreds, we're going to use their weights. So we need to keep track of those. Cool. Are there any other questions I've missed that people might be able to think of involving this project? We should also, talk about how this project, we should also talk about what samples or what signals this project won't work on. So I think it was brought up last night by Cameron that it won't work on population models. And the reason it won't work on population models is because if our split was right here, if you built a dictionary out of this signal, you wouldn't really be able to, the dictionary isn't able, we can't assume that the dictionary before this marker of the first endpoints should be like that of the next M time points. Very biased. It would be very biased. And this is a strong evidence of the biases. Another bias is in that we're assuming that the signal is uniform enough such that what we've seen in the past isn't uniform. It's biased because we're assuming our signal is periodic and the dictionary used to build it in the first n time points will be applicable to that of the next m time points. Because it's univariate, we're limited in that way. But if we introduced a multivariate analysis where we looked at other factors, so if we were predicting ECG, but we had other modalities such as heart rate and blood pressure and ECG we could use that to understand this, to explain the variations that otherwise might be confused with small errors. What I mean by this is, say like we'd expect the signal to be this green error, this green signal right here. But if we see this pink, if this pink is predicted, we can't say, oh, it's only due to error. There might be some other variable that might explain why it's going up so drastically, and it might be that the user, it might be that the patient was fed a drug, and that's what caused it to rise so drastically. And it's actually as accurate as you'd expect it to be. Obviously, then we really wouldn't be seeing the black area, but the black would then be this right there instead of down here. Cool. So we have to talk about that, and I think incorporating a multivariate model or multivariate analysis would allow us to explain those variations you otherwise wouldn't be able to see in a univariate analysis. Oh, and something else I didn't mention. So I brought this project up to my co-op boss named Dick Moberg. You go to like moberg.com. His last company built this ICU monitor that would time synchronize and harmonize signals and processes in the ICU. And he sold that company, he left the company, and his new company is analyzing that data. So what's most likely going to happen is the tool we're making for this project is going to go directly into his machine, or not his machine, the product we're working on, which I think is pretty cool. It's going to become an app on the dashboard that we're building.
That is cool.
Yeah, it is cool. We're going to be using it in our software if it works out well. What that means is that we have to do a good job. We're only going to deploy it if it works really well. He mentioned a possible way for me to give out rights to the data we have. So we have data on IBM from different clinical trials, namely like Track TBI. That was like a multi-center, multi-site, international trial of traumatic brain injury. And we have so much data. So I'm kind of working on that. So we have access to physiological data as a club in the future. And that's why I'm not worried about the conference situation, because Dick is always looking for new conferences. For instance, I'm sending this machine learning project to the the conference at Temple that's due on the 1st, and it's on predicting physiological incidents. So whether or not a specific modality will go above a threshold in the future. So yeah, I think that's really exciting. And anyone who's interested in AI, I definitely look at this company in the future for. I definitely look at the company in the future for a co-op position, because we're always looking for more people. And I have a feeling I'll be with them for a while. Kind of like it there.
So what do you do there for your co-op? Is it just working on the ICU stuff? Or? So
what I'm doing is I'm working on the development of software we're using. I'm working on cloud I do work on the cloud architectures. Right now I'm working on deploying and connecting different modules. So I've been working back end. We have a front end guy, so I'm trying to create API endpoints that he can hit, creating modules and apps that can interface with the dashboard we're building, work on AI projects. So this one was effectively trying to look at if we can engineer different metrics across 7 different modalities. Can those 7 modalities improve, or how well will they be able to use together to predict a given modality? So I was looking at these 7 modalities in predicting like ICP. or ABP. Andy, I will share it with you after I've submitted it to the conference. Thanks. Yeah. So yeah, good co-op. I'm trying to get it connected with Drexel AI. I actually put our club's name on a report that he's giving for like the second year of his grant, because I'm mentioning this project as something that is in collaboration with his company, just to strengthen what we're working on. Yeah. So that's it for me. If you have any questions, just like let me know what you should work on. I think, what's doable is the background section, because that's where we're gonna have to get a bulk of the related work. I know Safik mentioned he did some background reading. And he did the conclusion. Thank you very much. Alicia also mentioned interest in the background section. Alicia, I think you go more in the methods with time series forecasting. One person a while ago gave a good presentation on genetic algorithms, so they could talk about that. I could give my hand at sparse coding if no one else wants to. And then the introduction really should just be like a summary of the work from start to finish. That's kind of how I think about it. And then the experiments and results, we can maybe talk about the experiments we're running. The experiments are pretty straightforward. We're effectively just generating a training and testing set and running the pipeline that I've kind of been outlining for a while. And it's outlined in this Python document here. So yeah, cool. That is it for me. If you have any questions, I'll be sticking around for a bit. Otherwise, I'll see you next Tuesday. Hopefully by then we'll have the sparse model running, we'll have more of the paper done, and I'll have maybe even more information for you about like the IEEE Drexel thing or whatever. Cool. I will see you all next time.
See ya.
Yeah.
Ethan, hello.
Yes.
Can you hear me?
Yes, I can. Quietly, but yeah, I can hear you.
Yeah, my mic's been off. So can you please send me the link for the genetic algorithm slides?
Oh, that's a good question. The slides from that PowerPoint that someone did.
Yeah.
Okay. I would if I don't remember who presented. A, B.
I think it was Andy that made it, right?
Okay. Andy, did you present the genetic algorithms?
Oh yeah, the slides. Yeah,
yes.
Sure.
Could you send those to Ansh through Slack or something?
Yeah. Okay.
Okay. Thank you. And then maybe you two can collaborate on that section, because Andy, you did a pretty extensive job researching. So I'd like you to include, your work and thoughts as well. Ansh, I appreciate you helping out too.
Great.
Cool. Yep. Okay. Well, people have questions, so what's up? Fire away.
Also, did you think anything about like where we'll be publishing our proceeding?
Oh crap, I forgot. So
Yeah.
yesterday was the due date I set for myself for everyone to reformat their proceedings. Someone should have told me. Oh goodness. And
I just saw the message.
and I got them all back. Suffolk, you sent some conferences.
I did.
I appreciate that. So I kind of gave them the IEEE. So, okay, we did this backwards.
Yeah.
I gave them the IEEE template, so it's all in IEEE. So I think we should just go for that.
Yeah.
If not, we could just put it on, what's it called? Archive, and just, not put it anywhere, but just have it on archive. So it's technically published, but not peer reviewed.
Yeah. But I think IEEE is pretty chill with publishing.
Yeah. Are you familiar with their process?
Oh yeah. Like I am not I wasn't a part, but I know how it goes.
Okay. So then I'm sure I just take all of them and I just put them in a document, and then we have to fill out some stuff about the conference and what happened.
Yeah. Maybe you could just shoot an email to the guy. There is an email ID given at the bottom of the page, and you could just shoot them an email that we did this conference and we have all that stuff, and then they'll probably tell what's the next step.
Yeah. Let me look.
Yeah, I can
Yeah, I see it. I will. Yeah, IEEE is ready to help. Help. Cool. Yeah. I will. I don't know if that's something you can do beforehand. Who's the? Wait a minute, Civic. What's your position here? Are you the treasurer?
Yeah.
Who can I delegate this out to? I think I'll look into it. If someone else was looking into it as well, that'd be great. So that in case I miss anything.
Okay, I can help you with that.
Okay, thanks, man. But I'll also look into it because I think it's kind of important for me to learn, considering whole club thing. Cool. Yeah. Thank you.
Also for the sparse coding, for the background, I was reading through a few research papers, and I saw like most of the applications have been in the imaging section.
Yeah.
So are we putting those citations in?
Yeah, because we want to talk about related work because that's what's known, right? And we want to be able to talk about what's in the future. Alicia, also, I had a conversation with Edward Kim about a possible project of using sparse coding in genomic data, which I think is pretty exciting. Yeah. It's related to what I don't think you were in that meeting this past Saturday, but I have a feeling that I'll be working on that in the future. Just a heads up.
I saw this like paper on using sparse coding for the MRI scans, and it was like so cool.
Yeah. I mean, you can once I figure out like Osamu's pipeline or whatever he did, I'll distill it down so other people can understand.
Yeah.
I'll be the middleman.
Yeah.
Cool. Yeah. All right.
Okay, so I have like 9 citations so far for this sparse coding, so I think that would be enough for the background.
And then you know how to format in BibTeX like I did in.
Yeah.
Cool. Yeah. Cool. All right. Who's next?
Okay.
Do you have a question, Alicia?
Well, I was waiting for everyone else if they had questions. Other than that, okay. I was gonna go if no one else had anything.
Yeah.
The same, man.
Okay. Bye, Andy. Cool. Mahir, do you have a question?
No, not exactly.
Okay. Cool. Ryan, you good? Ryan disappeared. Pranell?
All right. What was the question?
Do you have any questions for me?
Oh, no.
Okay. So we can share. Pranell?
I know.
No? Okay. We're all good?
Okay.
Yeah.
Cool. All right.
I'm gonna go.
Me too. The meeting's over. Okay. Right. Bye, guys.
See you guys.
Yeah.